So this is the first real homework. That's also out. Homework is due in a week from today. It's mostly a review. Just make sure that you're keeping up with the material. The lab requires you to do some programming. You can use the same groups you used for the previous lab/programming assignment. Okay, so keep an eye out for more on the lab in the discussion section. We will give you a lot more detail at that point. All right. So what we are going to do today is continue the discussion on process management. Okay. Last time, I don't have a recap slide here. Last time we talked about basically process management. How do you create processes? How do you using fork, exec, wait, PID, all of the system calls to do process management. I talked a little bit about the notion of a context switch. Okay? Context switch allows you to the kernel to switch from one process to another. Okay? So we are going to build up on this notion of a context switch and talk about scheduling algorithm. Okay? Whenever a context switch happens, how does the kernel decide which process to execute next, which process to schedule for execution next? Okay? That is what CPU scheduling implies, and that's what we'll talk about today. So pay attention because this lecture is going to involve a bunch of class exercises. Okay, so you need to participate as well. Okay, so I'm going to start with some motivation for, again, what scheduling is, what does it do, and so on. So we have assumed a multi-program system. Okay, a multi-programming implies the ability to run multiple processes in your system all at once. Okay? If multiple processes are actually running, they need to take turns actually executing on the CPU. Remember, we are still assuming there's only one core or one CPU in the system, multiple processes. If they all need to run, they have to take turns to run. Okay, that's what CPU scheduling will actually do for us. Yes, and the reason we have multi-programming is the system can overlap I/O and computation. When some processes are doing I/O, others can actually run on the CPU and make good use of both the I/O devices or I/O resources and your CPU resources. Okay? This is the picture of the state transition diagram for processes I put up last time, and you will see that for each state there is a queue. Okay? So any process in that state is its process control block is going to be put on that. Okay? Remember, I said uniprocessor, so the run queue is at most one in size, as you can see there. Okay, so the question is, given a ready queue, you have a set of processes that are ready to run. Which one are you going to pick from here and actually schedule for execution? Okay, so that's what we are going to discuss today. Okay. So a few definitions about scheduling. Okay, so we'll distinguish between what we call long-term scheduling and short-term scheduling. Okay. So long-term scheduling is basically the problem of deciding how many processes actually get to run in the system. Okay. There are some limits on how many processes you can run without having bad things happen in your system. Okay. So, I mean, typically you can run tens or hundreds of processes, but there is a limit based on the hardware resources. One of the key constraints is the amount of RAM you may have, okay, amount of main memory you may have. If you have, let's say, 4 GB of RAM, that puts some restriction. If you keep on starting new processes, each process will get less and less memory, okay, because you have to basically have all the processes be given some memory. And you will eventually reach a point where the performance of your system is going to reduce dramatically. Okay? Same is CPU. Okay? If you start lots of processes, each has to take a turn at the CPU. And if you have a very large number of processes, each ready process may have to wait a long time before it gets to run. Okay, and your system starts becoming less responsive. Okay? So based on the hardware resources in your system, the OS tries to enforce some upper bound on how many processes get to run. Okay? This is referred to as long-term scheduling. Once you hit that bound, even if you start new processes, the OS may say, I'm going to let it wait for some other process to finish before I'm going to schedule for execution. So it may just sit in the new state, for instance. It will never go to the ready state because it's waiting. Okay. Or the OS may simply say, try again later, not enough resources. Okay. So there is a limit on the number of processes based on the amount of CPU resources or memory resources you may have. That is referred to as long-term scheduling. Okay? Now that's all we are going to say about long-term scheduling in this class. We are not going to actually go into details of how do you decide these limits and so on. All we need to keep in mind is there is a long-term scheduler that tries to ensure that the number of processes that you actually, active processes you have in the system, can be reasonably run. Okay? They can get reasonable amount of resources, they are reasonably responsive and so on. Okay? So, and we do this by enforcing an upper bound, so there is no overcrowding in your system, essentially. Okay? So what we are really going to talk about is what we call short-term scheduling. And that's the problem that I just mentioned. How does or should the OS select a process from the ready queue to execute? Okay? If you have more than one in the ready queue, which one gets to go next? Okay? And what are you trying to achieve by deciding among them intelligently? Okay? So we'll talk about goals. Okay? So you'll see that there is not one answer to this question, but there's a range of answers. Okay? And you'll have different scheduling policies or scheduling algorithms. Each will try to optimize a certain metric in your system and try to achieve a different goal. So let's first look at goals. What do we want to do by, or what do we want to achieve by short-term scheduling? We'll look at some options that are available, and then we'll actually look at policies and implementation issues and whatnot. Okay, so going into a little more detail, okay, the kernel has a CPU scheduling algorithm. Okay, this algorithm is going to run every time one of these three events happens. Okay? The process actually executes an IO instruction, and as a result, it goes from the run state into a wait state. Okay? At this point, the CPU becomes idle because the process that was running decided it needs to do some IO, it's gone to wait state, CPU is idle, the kernel needs to decide what to run next. Okay? That's the first of the three conditions that will actually trigger the scheduler. Okay? The other one is an interrupt occurs. When an interrupt occurs, basically that raises a trap. The kernel runs, the kernel processes the interrupt, and once it's done processing the interrupt, it has to then basically decide which process is going to run next again. Okay? The CPU scheduler will also run in that case, and whenever a process is created or terminated, the scheduler gets to run as well. Okay? So a scheduler will run every time one of those three things happen in your system. Okay? Now, depending on what short-term scheduling policy you have, we are going to distinguish between a non-preemptive system or a non-preemptive scheduler and a preemptive system or a preemptive scheduler. Okay? Now, as the name suggests, in a non-preemptive system, the scheduler will never interrupt a process by itself. Okay? It will always wait for one of those three events to actually happen before it will run. Okay? So once you schedule a process on the CPU, until that one of those three things happen, the scheduler will just let that process run. Either the process is going to do an IO, or it's going to terminate, or there's going to be an interrupt. Unless one of those three things happen, the process can run for an arbitrary amount of time. The scheduler will do nothing. It's not going to preempt that process. That's why it's referred to as a non-preemptive system. Okay? In a preemptive system, on the other hand, as the name suggests, the scheduler or the OS kernel is allowed to preempt processes. It is allowed to interrupt processes, okay, by itself, even if none of those things have happened. Okay? And this is basically what is going to be used to do fine time scheduling, as we will see. Okay? In particular, in addition to those three things, in a preemptive system, a timer may go off and say, this process has run for its time slice. Let's run something else. Okay? So you can then tell the process saying, now go back to the ready queue, I as the scheduler will pick some other process to execute next. Okay? So you can preempt a process just because its time slice expires. Okay? So in addition to those three things, in a preemptive system, you are allowed to interrupt processes, in particular when their time slice expires, okay, and run something else. Yes?
So what sort of interrupts occur in a non-preemptive system?
What kind of interrupts can occur in a non-preemptive system? Let's say you click a mouse button, okay? A network packet errors, keyboard clicks, all of those are interrupts. Okay, any questions here? So it's important to understand distinction between non-preemptive and preemptive schedulers, we will see variety of scheduling algorithms that you can use in either of those two flavors. Some will be only preemptive, others will be non-preemptive, some can do both or can work in either of those two environments. Okay, is that clear? Preemptive versus non-preemptive. Okay, so with that in mind, here are some things that we can think about when designing a scheduling policy. Okay, when deciding what process to run next, you want to think about what goals are you trying to achieve for your system. Okay, what metrics are you going to try to optimize? Metrics are just criteria. Okay. So you may say you want to pick a scheduling policy that will try to optimize CPU utilization. Okay. CPU utilization is the percentage of time the CPU is busy. You want to try to maximize the percentage of time the CPU is busy. Okay. When the CPU is idling, nothing useful is happening in the system. So if your scheduling policy allows you to maximize the usage of the CPU for a given set of processes, those processes are in some sense executing faster. Right? So that may be a good goal to shoot for. Another goal would be you want a scheduling policy that maximizes throughput. Okay? Throughput is simply the number of processes completing per unit time. Okay? You run some applications and over some period of time you see how many have finished. Okay? And the throughput is the number of processes that finished that divided by the total time that has elapsed. And that's the number of processes finishing per unit time. In some sense, the faster processes finish, the better you are doing in some sense. Okay, so you may want to optimize throughput. Typically, throughput matters only if you have more batch jobs. Okay? If you have interactive job, it doesn't make sense to say I want to pick a scheduling algorithm such that the browser process is going to finish. Okay, the browser process will run as long as the user, wishes for it to run. Okay, it has nothing to do with the scheduling per se. But if you have batch jobs, okay, the jobs that just do computation and finish without any user input, that's a valid metric to try to optimize, okay, finishing or maximizing throughput. Okay. You may want to say the scheduling policy should optimize the turnaround time. Right? Yet another metric, turnaround time is simply the time it takes to run a process from the start to finish. Right? So basically you take any process, see what is the time it started, time it finished. The difference between the two is the turnaround time for the job. That's the time for which the process was active from new to terminate state. Okay? If you want to minimize that metric, then you basically you have to pick a scheduling policy that looks at the turnaround time and tries to optimize it or minimize it per process. Okay? You may want to optimize wait time. Okay? That's the total amount of time the process sits in the ready queue. Okay? Let's say the process is ready to run. Okay, so just going back to the ready, when it's ready to run, it comes and sits in this queue and it waits for its turn to go and execute. Okay, trying to optimize the wait time simply says once you're ready to run, you will actually get scheduled in the shortest amount of time as per the scheduling policy. Okay, again, when you're waiting, nothing useful is happening for that process. So optimizing wait time is another good goal. We'll look at scheduling policies that explicitly look at that. Okay, and the last one is response time. Okay, response time can be defined in many ways. It is basically here, we define it as the time between when the process is ready to run and its next IO request. It could also be thought of as the time it takes for the process to respond after you provided some input. Okay, so you're looking at how responsive your system is. The more responsive it is, the better you feel. You feel that your system is running fast, is responsive to whatever you do. You don't have to click a mouse and wait for 3 seconds for the click to actually be processed and something to happen. Okay? So that's another good goal. In interactive system, trying to optimize response time is a good goal as well. Okay? So these are various metrics that you can think of before you decide the scheduling policies. Okay? Now you might say these all sound like good things to do. Okay? Maximize CPU utilization sounds good. Okay? Why not maximize the usage of the CPU, maximize throughput, okay, turnaround time, waiting time, they all sound like good goals. Why would you not try to optimize some of them or all of them? Yes?
For CPU utilization, is that really just situational? Because you do not necessarily want the CPU being busy all the time if you can avoid it.
Okay. Question is, when do you not want the CPU to be busy all the time? Right? It's a good goal to achieve now, but it also depends on what kind of system it is. If you're designing a system that is going to run primarily IO bound jobs, okay, then maximizing CPU utilization, is not necessarily the right goal. You may want to maximize IO throughput because most of the time your process is spending doing IO. Okay, it's rarely spending time on the CPU. So trying to achieve that goal when not very many processes are even trying to execute may not be the right thing to do. If you're CPU bound tasks, then maximizing CPU utilization is a good goal. So the answer is it depends on what you expect to see in your system and what you want to achieve. Okay, so ideally you may say you want it all. Why not pick some scheduling policy that tries to optimize all of them? Okay? Try to optimize all of those metrics. Okay? But this is where we have to look at trade-offs. Okay? It turns out that there is no scheduling policy that you can come up with that will optimize all of those metrics. Okay? There is no free lunch. Okay? You will optimize some metric at the expense of others. You may be able to minimize wait time, but that may impact response times. You may or turnaround time, as we will see. Okay. So you could minimize the response time, variance in the response. There are many metrics, but as it turns out, it's generally not possible to optimize them all. So you have to decide really what kind of system are you building. What is this kernel going to run on? Okay, is it going to run on systems that run batch jobs? Are you looking at interactive machines like a laptop or a tablet where there's a lot of user interaction? Are you looking at some other kind of system? Is it a server system? Is it a laptop? Is it a desk or some other kind of machine? Depending on what your machine is and what kind of workload it runs, different scheduling policies might be appropriate. Simply because there's no one policy that will optimize all of it. And the reason why there is no one policy can optimize them all is why when you try to make one of these things better, it always comes at the expense of something else. Okay? If you try to make this metric better, it may make some other metric worse. So you cannot actually make all of them, optimize all of them all at once. Okay. So I already mentioned you can minimize average response time. This is a good goal to shoot for in interactive systems, okay, where you have user input. Okay. You want the system to respond quickly to any user input. Okay. This is where you are minimizing the average response time. So the user feels like he or she has a responsive system. In some cases, you may actually not want to minimize the average response time, but you want to minimize the variation in the response time. Okay? And this is based on the observation that predictable response may be better than a low response but that has high variance. So if you have a system that sometimes when you click a mouse button, it responds almost instantaneously, and sometimes it takes 3 seconds. It's probably going to drive some users crazy because once in a while it looks like it's taking 3 seconds and press the mouse and you're waiting there and 3 seconds pass and then you see a response. Sometimes it looks like it's very fast. So high variation. Yes. As opposed to that, consider another system that always responds predictably around with an average response time of half a second. The claim is that predictability is sometimes better because the user gets used to it. That's the speed at which the system responds. And it's always responding at an average response with an average response time of, in this case, half a second. So rather than minimizing the average, it may be also good to minimize the variance. A slightly different metric. Okay? Maximize throughput, I already mentioned. If you have a batch job, okay, maximizing throughput, the number of jobs that are finishing per unit time, is a good metric to shoot for. You have jobs that are being submitted. This could be simulations, for instance, that you just submit a job. There's a long computation cycle, and then the job spits out some output. And if there are lots of just jobs being submitted, you want to maximize the number of jobs finishing per unit time so that the throughput is maximized. Okay? Or you may want to minimize the wait time. Okay? This is the time that you basically spend sitting in the ready queue, and that allows you to be fair. When we look at some of these policies. Okay. So in interactive jobs, focus on response time. Okay. Batch jobs, you have to focus on throughput. Okay. Wait time is generally a good metric to shoot for regardless, although you cannot pick all of them again. Okay, is that clear? Any questions on this? We haven't talked about a single policy yet. Okay, before trying to look at policies, we need to know what we are trying to do. Okay, what goals do we want to set for ourselves before we start thinking about how to schedule processes? Any questions on this? Okay, so we'll start talking about policies now. Here are the set of assumptions we will make. Okay, just to keep things simple, we'll assume there's one process per user, and all processes are single-threaded. There is only one thread per process. When we start talking about threading, we'll relax that assumption. But as of now, no threads, only processes, single-threaded processes. Furthermore, we'll assume processes are independent. They're not cooperating. If they're cooperating, you may pick policies that allow you to schedule groups of cooperating processes in some reasonable way. Here, each process is its own thing. There is no dependence between processes, so we can make decisions regarding a process independent of what other processes are doing. Okay? So these are the assumptions we'll keep in mind. Okay? Of course, relaxing all of these assumptions makes your policy more realistic. There are scheduling research being done even today, but we are going to only look at some simple ones. Okay? These are the few that we'll look at today. We'll start with some very simple ones and end up with some very sophisticated ones by the end of today's lecture. Okay? So I'll introduce those terms as we go along. So the first policy is the simplest you can think of. First come, first serve, also called FIFO, first in, first out. Okay? As the name suggests, first come, first serve simply says just schedule jobs in the order in which they're arriving in the ready queue. Okay? If there are multiple jobs queued up in the ready queue, pick the one that arrived first, schedule it. Okay? And pick the one that arrived next and schedule it, and so on. Okay? So the scheduler executes jobs to completion, okay, in arrival order. Okay? So that should immediately tell you this is a non-preemptive policy. Okay? Once you schedule a job, it's going to run through completion unless it does I/O in between or there's an interrupt, say. Okay? Non-preemptive. Okay? There is no time slice, there is no switching between jobs here. You schedule a job, it gets to run. If it's CPU bound, it will run to completion. It may take 15 seconds, it may take 15 minutes, doesn't matter. A scheduler is not going to interrupt that job and run something else. Unless it does I/O and it gives up the CPU. Then the scheduler can schedule some other job. Okay? So it is basically a non-preemptive system. Okay, here is a picture that shows how things work. It's very straightforward. So we'll assume there are three processes. Okay, I'm just going to call them jobs because that's a more generic term. You can use some of these policies for threads as well. Although today we are not going to focus on threads. I'll use this generic term jobs to refer to processes or threads. But for now, jobs are equivalent to processes. Okay. So we'll assume there are three jobs, A, B, and C. Okay. And they all arrive at time 0, but in the order B, C, A in the ready queue. So that's the order in which they get to run. Okay, B gets to go first. Let's say it needs 2 seconds before it finishes. So it runs for 2 seconds, then it finishes. Okay, it doesn't do any I/O, so it gets to run to completion. C runs next. It takes 3 seconds, it's going to complete, and then A gets to run next 5 seconds. Okay, so by T equals 10 seconds, all three jobs are done. Okay, and the FCFS scheduler just scheduled them in arrival order. They had also arrived at time 0, but in the order A, B, C, they would run in the order A, B, C. Okay. Now, if they arrived in the order A, B, C, but the job A does some I/O somewhere in between its execution cycle, you'll run job A until it does some I/O here. Time T equals 2 seconds. It gives up the CPU, goes to the wait queue, and the ready queue has only B and C. So you run B. Okay. So then B gets to run. B runs to completion. By the time B finishes, A has finished its I/O. It's come back to the ready queue. So your ready queue has A and C. Okay. B is done. So only A and C. Between the two, A arrived first, clearly. Yes, because it arrived. And then so you run A to completion and then C. Okay. So non-preemptive, except when you do I/O, you have to run something else. Yes,
Just
question.
to clarify here in the third one, the A came back before the C was put in the queue.
No. So C was actually in the queue. All three arrived at time 0.
I
Okay?
see.
So there's A, B, and C, all of them sitting in the queue.
Okay.
Okay, so you have to distinguish between what arrival order means. Are you looking at when the job arrived in the system, or are you looking at when the job arrived in the queue? If you distinguish between the two, then your confusion will probably get clarified. So in this case, A actually came in. Okay, so then basically it ran, and then we did IO here. Then B got to run. B was already there. Okay, and then A finished, and A has come back in. If you look at the order in which you are put in the queue, C is already in the queue, and A went after C. In that case, you would have to run C and then A. And this is FCFS as far as the ready queue is concerned. If you look at FCFS as far as arrival time into the system is concerned, then A has come in before C. So even when it gets ready to run next, it still gets to run before C, although C is already sitting in the queue. Okay? Is that clear? So based on how you decide what FCFS is doing, whether it's ready queue ordering or arrival time ordering, either of those two would work. Yes, question.
So if B wasn't over, would it resume after A? Or just B might
Okay, good point. So if B hasn't finished, but A is done with this IO and it comes back to the queue, what should happen then? That's the question, right? Okay. So as I had mentioned, this is a non-preemptive system. The scheduler does not get to interrupt the process saying something has happened in the system. Okay? Because it's non-preemptive, A can become ready to run anywhere in between and B will still have the CPU to itself. If this was a preemptive system, then you could have said, I will interrupt B and let A run again, for instance. But that's not the case here. Okay? That clear? Okay, I'll defer that question until we come back to an example. And then we look at it. Okay, so advantages is a very straightforward schedule. Simplest scheduling policy you can build. No intelligence. Okay, you simply look at the queue or the arrival order and say that's the order in which processes run. Okay. Disadvantage is that the wait time is highly variable in this case. Okay. If you are unlucky process that arrives just after a long process has arrived in the system, you have to wait for a very long time before you get to run. Okay. So basically you may be a very short process that needs very little time, but because you are scheduling processes in arrival order, you may be small jobs may be stuck behind long jobs. Just as if you're driving on the freeway and you get stuck behind an 18-wheeler, you become impatient. Small jobs are going to be impatient in the system, but they are out of luck. There will be highly variable wait times if the jobs are of unequal length. Okay. So basically that's the other point. There may be, as a result of this, there may be some poor overlap of IO and CPU. Okay, because the small jobs typically tend to be the IO bound job. They need short bursts on the CPU and then they go back to doing IO. There's a long running CPU bound job executing on the CPU, then the IO bound job, even if it becomes ready, may have to wait for long periods of time. And as a result, it's neither using the CPU nor the IO device and wasting resources. So it may lead to poor utilization of, or overlap rather, of CPU and IO. Okay, we'll see how subsequent policies will help us address some of these issues. Any questions here? Okay, that was the simplest policy. Next policy, round robin. Okay, so this variant of round robin policies are used in most systems today. Okay, somewhat more sophisticated variants as we will see later on in this class. So it's a fairly common policy. Okay. This one is preemptive. Okay, as opposed to FCFS, which was non-preemptive. This one is preemptive. Okay, so here you are going to add a timer. Okay. Each job is going to be given a time slice. Okay. You let a job run, you start a timer. The timer expires. If the job is still running, you basically evict it from the CPU, make it go to the end of its ready queue. Okay. So if you have a set of jobs in the ready queue, you are going to cycle between them. Give them each, let's say 10 or 100 milliseconds. So you run the first job for 100 milliseconds. Not done, you go to the second job. Run for 100 milliseconds and you just do round robin. That's what the policy is. Okay. Fairly simple. So after each time slice, you move the running job, thread or process to the back of the queue. Okay. So the policy is straightforward. Now the main issue is how will you decide the length of the time slice. And what should you pick? Should you pick 1 millisecond, 1 microsecond, 1 second, and depending on the choices, you will get a range of behaviors in your system. Okay? So here are the two extremes that are mentioned here. Okay? If you pick a very large time slice, okay, your basically waiting time is going to suffer. Because large time slices, if there are lots of jobs in the ready queue, each job has to wait until all the jobs ahead of it have finished or have taken one turn at the CPU, then you get a turn to run. So you start waiting for longer and longer periods of time because each job gets a larger and larger time slice. So all the jobs ahead of this job in the ready queue are all going to have to finish their time slices as hopefully, and then this job gets to run. Okay, so large time slice implies waiting time is going to suffer. And as you can imagine, as the time slice goes through infinity, as it becomes very large, this policy is going to degenerate to FCFS. If you pick an unreasonably large time slice, let's say you pick 1 hour time slice, okay, that's basically equivalent to FCFS because if you run a job which gets a time slice of an hour, many jobs may not take that long. Okay, so they will basically run through completion because the time slice is greater than the job length. Okay, so as the time slice goes to infinity, the policy degenerates to FCFS. Okay, so we just argued that large time slices cause a lot of problems. Okay, the wait times increases, the policy becomes less fair, etc. in terms of waiting times. So you might say that sounds like we should pick a very small time slice. If you have small time slice, none of those problems will occur. Okay. Now, indeed that is true, but if you make the time slice very small, what is going to happen is the number of context switches is going to grow. Okay, let's say you pick a 1 millisecond time slice rather than an hour time slice. So that basically says once a job is scheduled, it gets to run for a millisecond. Then it's context switched out, another job gets to run, and so on and so forth. Okay, so if you have 1 millisecond time slice, you'll have 1000 context switches per second. So that's a lot of context switching, and context switching incurs overhead because every time you switch from one process to another, you have to save the state of that process in the PCB. You have to load the state of the next process from the PCB. That's all bookkeeping overhead. Okay, so the context switches are essentially a tax that we have imposed on the system for the flexibility of switching from one process to another. Okay. So the smaller the time slice, the more the context switch overhead. Okay, more time you're spending switching between processes because there's a lot more switching going on. Is that clear? So what would you do? I just said large time slice, we don't like that the wait times have increased. Very small time slice, we don't like that there are too many switching context switches and that imposes needless overhead on the system. Yeah.
Is there a way to predict how much time a certain job might take?
Okay. Can you predict how much time a job can take? You could try, but the OS will never actually know what a job does because the job is not going to tell the OS. You could try to guess, but even if you could guess, then what would you do? Let's say you could predict in the ideal world. How would you use that to make the scheduling better?
What if you knew that job would take a lot of time doing IO, schedule a short job?
Okay, so what you are saying is if the job might take do IO, you may want to schedule it first and so on. You could indeed do that, right? But that's not a round robin policy. That's actually what you just described would actually give us a different scheduling policy. The one that tried to favor IO bound jobs or CPU bound jobs. In fact, we are going to look at some similar policies next. Right? All we are trying to do here is not try to say how do we decide on a different policy. Assuming you're stuck with round robin, how do you decide what time slice to pick so that it performs reasonably well? That's all we are trying to say. Yes.
Is it always a constant value or can it vary and adapt as it needs to?
Okay, so question is, can you make the time slice change over time? you could do that. The policy becomes a lot more complicated. You have to decide when to make the time slice bigger, when to make the time slice smaller. We will actually see a variant of round robin policy that uses different time slices for that very reason. It doesn't actually change it on the fly, but there is a number of different time slices to pick from. Okay, but they're statically decided. Okay? But that again is not simple round robin. It's a more complicated policy. Yes.
You decide based on whether you want a low waiting time or a high throughput and balance it between.
Okay. So the simplest thing is if you say you are either if you do large time slices, the waiting time suffers. Or small, the throughput suffers. Okay, you are stuck. Okay, you have to say which is the lesser of the two evils. What am I going to live with? Am I going to live with more context switches, or am I going to live with worse waiting times? Okay, and that's what you are going to have to do. And you could say, I don't want to, basically, I can pick something in between, neither too large nor too small. That tries to basically say, there is some wait time, but it's not too bad. There is some context switches, that's not too bad either. That's what I can live with. You can either go to one extreme saying, I don't care about wait times. I'm going to basically make it very fine and pay the price of lots of switches. Or you say, I don't care about wait times, so I'm going to basically make it very large. Or you say, I don't want to make either of those two worse because they are both bad from some perspective, or the other, I'll pick something in between. So this is basically all the design decisions a OS designer has to do. If you are a kernel designer, you have to pick the time slice, default time slice. That maybe a sysadmin might change, but you always have to provide a default. The default has to be chosen based on what you expect the system to do and what you want to live with. Okay? So typically what you will do is pick something in between. In some sense, you want to balance these trade-offs. And what you will say is, I'm willing to pay a price of 1% tax on the context switch overhead or some such thing. Okay, meaning that the context switch is roughly 1% of the time slice. You will say, how much time does it, how many CPU cycles does it take to do a context switch? Okay, let's say it takes 10,000 CPU cycles because of saving, loading registers, and doing all the other bookkeeping. And you say, I make the context switch large enough so that's approximately, that tax is 1%. Okay? So my degradation in this case is 1% because of the context switches. Okay, so this is one way by which you could decide. Yeah. Now in most systems today, you see context switch, rather time slices that are in the 10 to hundreds of milliseconds range. Okay. I think I mentioned last time, if you take the Linux scheduler, it has made a decision of using 200 millisecond time slices. Okay. So basically you can have at most 5 context switches per second per core. And so there are some others that may have picked 10 milliseconds. That will give you up to 100 context switches. But that's the rough order. Okay, you don't choose in the seconds, you don't choose in the microsecond. Okay, you pick in the tens of milliseconds. Okay, that gives you a rough balance between these two matrices for today's CPUs. Okay, so very quickly, advantages, it is fair in that every job gets a shot at the CPU. You are cycling between processes, you are not favoring any one of them. You're just simply going in order and giving each of them a turn at the CPU. Okay, so it's fair in that sense. Disadvantage is that we'll see that average wait time can actually be bad in some cases. So here's the first of the in-class examples / exercises. We will now start comparing. Okay, rather than me just saying this is good or not good, we are actually going to take some jobs. We are going to use each of these policies to schedule them and understand how they behave. Okay, what are we seeing in the system? This is actually going to show us, hopefully give us a little more insight into how these policies perform. Okay, so 5 jobs, 1 through 5. Okay, each has length of 100 units. Okay, let's say it's second, it doesn't matter. Okay, 100 second jobs. Okay, we are assuming that if for round robin the time slice is 1 second. Okay, there is no context switch time. You're going to ignore the context switch altogether here. So context switches are instantaneous, they come for free in this system. That's not true in practice, but for this exercise we'll assume it's 0. Okay. So now let's just schedule them by using FCFS. Okay. So which job will finish first when you do FCFS? Somebody said something.
I just said
One. Do you say
one.
something?
Depending, I mean, if they came in 1, 2, 3, 4, 5.
Okay. So you should have said what order did they arrive in. You can't say what order they finished before you know what order they came in, which I actually didn't say at all. So let's assume they came in this order. 1, 2, 3, 4, 5. They all arrived at time 0, but in that order. Okay. So now that I told you which order they came in, should be straightforward to apply FCFS. Okay. So job 1 came in first, it's going to be scheduled first, and as a result, it's going to finish first. There's no IO here. Okay. So job 1 will run through completion and it will finish at what time? 100. Okay. You start at 0, so it needs 100 seconds, so it's going to run and it's going to finish at time 100. Okay. Then job 2 is going to run. This is FCFS. Okay, so job 2 starts at a time 100 and it's going to finish at 200. Okay, it needs also 100 seconds on the CPU. And then this is going to take another 100, 100, 100. So the last job is going to finish at time 500. First job is going to finish at time 100. And each of them finish 100 seconds apart. Okay, so that's FCFS. That's trivial. Well, let's do round robin. So which job is going to finish first and at what time?
One at 500.
One is going to finish at 500.
495.
495, right? Somewhere in that range, between 495 and 500. So you have to say, how is round robin going to work? Okay? It's going to run each job one at a time and give each of them 1 second. Okay? So it will run job 1. So they've arrived in this order. So they are sitting in this order in your ready queue. Run job 1. Give it a second. Okay? And say, is it done? It's not done. It needs 99 seconds more. So you evict it and make it go to the back of the queue. You run job 2. Give it 1 second. Okay? And then at the end of that second time t equals 2, it's going to get evicted. And 3 is going to run 4, 5. So after t equals 5 seconds, each of these jobs have run once on the CPU and they have gotten 1 second of CPU time. Because that's the time slice is 1 second. Okay. And then you repeat. So each of them now needs 99 seconds of more computation. Okay. So you're going to do a second round. At time 10 seconds, they would have each run twice on the CPU, gotten 2 seconds of execution time. So there's 98 seconds remaining. You keep doing this, and then you will see that at time t equals 496, okay, this job is going to get its 100th time slice and is going to finish. So it would have gotten 100 seconds of execution time. Okay? So this job finishes at 496. This job finishes at 497, 498, 499 and 500. At time 500, all of those jobs are done. Okay, so that's what's shown here. So FCFS, you finish 100, 200, 300, 400, 500. Average time is, you just take the mean of those, that's 300. Yeah. You do round robin. Now each of them is executed. You will see that now job 1, although it arrived first, is actually they are all finishing very close to one another. 496, 97, 98, 99, 100. The average is 498 there. Okay, so completion time has gone up in round robin. Okay, so if you wanted to optimize turnaround time, which is completion time, that's not happening anymore. But you can see inherently that this is fair. Yeah, if all those jobs arrived all at once, they all get a fair share, and then you each give them 1 second and each gets to run and so on. Okay, so it's more fair, but at the expense of some other metric, which is the completion time. Okay. There's another column here which is called the wait time. Okay. As I mentioned, wait time is the time you spend in the ready queue waiting for your turn to run. And then the question is, in FCFS, how much time did each of these processes sit in the wait queue? And in round robin, how much did they actually spend in the wait queue? Okay, the answer is already there, but let's ask the question, how do you actually find it out? How do you compute that value? Yes.
That something else is running and it's included.
Can you speak up a little?
The time that process A isn't running, but waiting for process B to finish, and it's not ready.
Yes. Can you express that in a formula? So you can always figure it out regardless. There's a very simple way to figure this out if you think about it. Yes.
Completion time minus process time.
Okay. Completion time minus process length. So assume they all arrived at 0. So if I tell you this process arrived at time 0, it finished at, let's say, time 200, and it ran on the CPU for 100 time units out of those 200, and I asked you, so how much time was it waiting in the ready queue? What would you say? Not clear what I just said. So let's say a job arrives at time 0, and I say it finished at 200. Okay, so it came at time 0, it finished at time 200, and I say of those 200 seconds, it ran on the CPU for 100 seconds. And I say how much time did it spend waiting? You will say 100, because of the 200, 100 was spent on the CPU, so the other 100 must have been waiting, it was not doing anything else. Okay, so that should tell you the simple formula that I just mentioned here is simply wait time is finish time minus execution time. Actually, so this is what we just said. I said finished at 200, it ran for 100, so the rest of the time it waited. Now this is, you can actually extend this because this only works if they all arrived at 0. So you should say minus arrival time. Okay. If you blindly apply this formula, it doesn't matter what the scheduling policy is, because you just say what time did it arrive, what time did it finish. Of that duration, how much did it spend on the CPU? Everything else is wait. Okay, so wait time is completion time or the finish time minus the time for which you actually ran on the CPU minus the arrival time. In this case, arrival time was 0, so we just did this. Okay, so simply speaking, this column should be the difference between these two values. This is the completion, this is the execution. Okay, so 500 minus 100 is 400 and so on. And the same is true for round robin. Okay. So the difference between these two columns is the wait time for round robin. Yes.
So if process is sitting in the new queue, it's still considered to be waiting.
So question is, the process is sitting in the new queue, is it still waiting? It is actually waiting. In this case, we have ignored context switches, we have ignored waits, we have even ignored the actual time doing IO. This is a highly simplified version. Okay, so in some sense, you would have to account for that. Those would not be times spent in the wait queue clearly. But here we are going to say it is all waiting. Other questions on this? So we are going to pick up pace a little bit here. Okay, second example, we will do this much faster than the first one. Okay, so again, 5 jobs but now of unequal length. Okay, again they all arrive at 0 in that order. Okay, and going to schedule them in FCFS and round robin, no IO. A simple version. Okay, so which one will finish first in FCFS? Job 1. Okay, because that's the order of arrival. So it's going to finish at time 50. It arrived at 0, it's going to run, finish at time 50. Job 2 finishes next, okay, at time 90, 120, 40, 150. Okay, so that's simple. Now think about round robin. Which one is going to finish first? Someone said 5. I don't know who said this. 5. Can you elaborate a little?
Yeah, they can reply to 2 and 10. So the cycling of the OS is not going to take a long time to go back to it.
Okay. So as is pointed out, what does round robin do? It just goes in order, gives each of them 1 second. Okay? At the end of the first round, each job has gotten 1 second on the CPU, and each, so you decrement the time remaining. So this one is 49 more seconds, this one is 39, 29, 19, 9. Okay? Repeat. The end of the second round, this one is 8, 18, 28 and so on. Okay? You keep doing this 10 times. Okay? This job would have gotten 10 time slices of 1 second each. Okay? So after 10 rounds of scheduling each of these jobs, the fifth job would have gotten 10 cycles. It's going to end. Okay? So it will actually end at 50 because each cycle takes 5 seconds. Okay? So then this job is done. Okay? It's no longer in the CPU, on the CPU. Now you do round robin among the remaining 4. Okay? So at the end of 10 rounds, this job needs 10 more seconds because it's gotten the 10 out of its 20. This needs 20, 30, 40. So you repeat. Okay? Now each round is taking 4 seconds because there are only 4 jobs. But you need 10 more rounds to go because then this one is going to finish next. And so on. Okay, is that clear? So you have to work through this a little bit on paper and pencil, but that's essentially what's going to happen. So if this job is going to finish at 50, it's gone. Then you do round robin among the remaining 4. Okay? And then that's going to finish at 90 because each round now takes 4 seconds rather than 5. There are only 4 jobs being scheduled. Each gets a second on the CPU. So that 10 cycles takes 40 seconds. So this one is going to finish. Then you do these 3. Okay. So you will see that here you are basically this order is simply getting reversed here. The average here is the same. So you do that 50, 90, 120, 140, 150 and that's the reverse. Just artifact of the job length. Okay. Wait times, we simply plug this formula in. Okay. You take the difference between these two, that's the wait time. Take the difference between these two, that's the wait time. Okay. Anything I should clarify? Okay, this requires you to actually execute round robin on paper. Okay, to sort of figure out in what order they finish. Okay, so next up, different policy called shortest job first, SJF. Okay. Simple policy, it says look at the ready queue. Pick the shortest job in the ready queue, run it next. Okay, that's why it's called shortest job first. Okay. There's a variant there called SRTF, shortest remaining time first. I'm going to come to that in just a second. Okay. Shortest job first is a non-preemptive policy. You pick the shortest job, you let it run to completion. You don't preempt, there are no time slices. Okay. It's clear what shortest job first does, right? You look at the ready queue, say which is the shortest job, and you're going to run it next. Okay? Good thing about this policy, it is the best policy if you want to minimize or optimize your wait time. It's provably optimal. You can prove that there is no other policy that can actually do better in terms of minimizing the average waiting time in the system. Okay? You say you want a policy that optimizes wait time, this is the one to pick. That's the one that is going to give you the best. Another advantage is it works for preemptive as well as non-preemptive schedulers. Shortest job first is the non-preemptive version. If you wanted a preemptive version, you add time slices. So what you do is you basically pick the shortest job, run it for one time slice, and at the end of the time slice, you put it back in the ready queue, and you look at all the jobs again. Okay? If some other job is shorter than this job, it will get to run next. If this is still the shortest job, it gets scheduled for execution again. So you make this decision repeatedly at the end of each time slice. Okay? And you look at the shortest remaining time because that since the jobs are running, we are going back to the ready queue, you say how much time does this job need beyond this point, and you pick the one that has the shortest remaining time, which is essentially the shortest job. Okay? So it works in either of those two models. You can have a preemptive version and a non-preemptive version. Okay. The preemptive one is called shortest remaining time first. We'll do some examples. Okay. Now the other claim or other advantage of this policy is the IO bound jobs get priority over CPU bound jobs. Okay. As a result of this policy. Okay. Question is why? You just said pick the shortest job. Why does picking the shortest job imply that you are favoring IO bound jobs over CPU bound jobs? Anyone have a thought on this? Yes.
CPU jobs have more CPU time than IO bound.
Okay, CPU bound jobs may need more CPU time than IO bound. There's a hand here in the back. Anything, go ahead.
Scheduled based on the amount of work until its next IO request. So if there are jobs with equal CPU time, but one has IO request in the middle, it will be scheduled first.
Okay. So 2 points being made. One is CPU bound job imply that the job is going to spend more time on the CPU and hence must be longer. The other point being said is if it's an IO bound job, okay, you basically pick the length of the job is defined as the time you need until you do the next IO. Okay. For a CPU bound job, it doesn't do any IO, so you just find the time to completion. For an IO bound job, it needs very short periods of time on the CPU and then it goes back to doing IO. Okay. Both of those observations are right. In fact, they are just looking at the picture in two different ways. So IO bound jobs, if you think about what they do, they spend most of their time doing IO, and in between two IO requests, they may spend a little bit of time doing some computation, and then another IO instruction comes in and they go back to doing IO. Okay. So if you think of a timeline, okay, so this is time. If you look at an IO bound job, it may do IO, CPU, IO, CPU. So this is how it's going to behave. It's going to spend long periods of time doing IO, then it becomes ready to run. It does a little bit of computation, another IO instruction is triggered, another long IO, and so on. So they are very short computation bursts, and then they do IO. CPU bound job is the exact opposite. So they spend long periods of time doing CPU. They may do occasional IO or no IO, but if they do occasional IO, it does a little bit. And then they go back to doing computation. Okay. That's basically what IO bound and CPU bound jobs look like. Next question.
So would a job that does lots of little I/O requests, would that tend to starve the CPU, cause the CPU bound jobs to starve more than a job that's I/O bound in the sense that it does a few very large I/O requests?
Okay. Good point. Point is the question being asked. We have a recursive question stacked up to answer. This question is, would a job that does lots of little IOs but also small computations between those IO starve longer CPU bound jobs? Okay? Because we are favoring shorter jobs, shorter computational jobs. So will we basically end up starving the bigger jobs? Okay? The answer is yes, and we'll come back to starvation in just a second. We're still here. We'll come back to here and I'll answer that again. Okay? Right now, I'm just trying to get you all a feel of why are we favoring IO bound jobs. Now it should be clear. If I simply pick the shortest job, which one do you think is shorter? Okay. This is what an IO bound job looks like. This is what a CPU bound job looks like. Okay. Even if you sum up all the CPU cycles this job needs, it's going to be much less than a CPU bound job. Okay. Because you need a lot more CPU time than an IO bound job. Okay. So by definition, if you just look at how much CPU time this job needs, an IO bound job is typically going to need less than a CPU bound job. So by simply picking the shortest job, we have started favoring IO bound jobs in the system. Okay. Whether it's a good thing or not, we'll discuss. But you should realize that our shortest job first policy is going to actually start favoring IO bound jobs. Yes.
You're saying that they're favoring IO bound jobs simply because of the because of most of them tend to be large IO, small computation.
Yes.
But if you have large IO, large computation, there's no favoring towards that.
If there's large IO, large computation, it's a mixed job. So you will not necessarily favor it. You will still favor the. It depends on what else is in the system. Right? So you won't favor that kind of.
So it's simply a coincidence, sort of.
It is
Okay.
simply a coincidence. You said shortest job. It just turns out that this job needs shorter. So let's say it does 9 seconds of IO and 1 second and 9 and 1. So this job needs total of 2 seconds, okay, of CPU 1 and 1. And here let's say it's the opposite, 9 CPU 1, 9, 1. This job needs 18 seconds. Between these two you'll pick this. This is shorter. Okay. So now you pick that IO job. Yes.
How do scheduler know which?
Good point.
Has
So.
the least amount for
So good question. How do you know which of the jobs, which is a shorter job? Okay. So there are two questions. I'm going to answer both of them in one shot. Both are actually disadvantages. that are actually mentioned here. The first thing is, although this is an optimal policy for waiting time, it is not possible to implement it in any real system. It's impossible to implement. Okay? The reason is exactly what was asked here, because you say, how does the scheduler know what is the length of a job? You start a process, you double click on Internet Explorer or Chrome. How does the scheduler know how much CPU this process is going to take? It doesn't know what the user is going to do. It can take a guess, but it's just a guess, it's not a definitive answer. You just start up, when you start up an application and make it a process, OS has no idea how much time this process is going to take. It could take a little bit of time, it could take a long period. You don't know. Okay? So in practice, it's impossible to actually implement this policy because it requires knowledge of the job length. Okay? Only if you know the job length can you pick the shortest job. If you don't know the job length, you cannot decide which is the shortest job. Is that clear? So this policy, although it's a good one to optimize waiting time, it's optimal, we can never implement it in practice. Only way to implement is to tell the user, say, when you start your application, tell the OS how much CPU time it's going to take. And then you tell the OS. How does the user know? User doesn't know or even care about the CPU time. They just want to do something with their application. Okay? So unless this information is provided to the kernel somehow, it cannot schedule those jobs. Okay? Impossible to implement. That's the first point. Okay? Second point was the question what was asked here, saying it has another bad property, which is starvation. Okay? Every time this scheduler runs, it is simply going to pick the shortest job. Okay? Let's say that a long job arrives in the system. Okay? But there's a short job waiting also. Okay? CPU scheduler runs, it picks the short job. Okay? Now the short job may finish, but now when the CPU scheduler runs again, if another short job has arrived in the system, again that short job gets favored. So there's a constant stream of short jobs coming in. Okay? The long job is just going to sit there because there's always something that is better from the CPU scheduler's perspective, a shorter job. Okay? So this long job may never get to run, it will starve. Okay? The policy has starvation problems. Okay? It doesn't ask how long has this job been waiting, so even if it is long, let's schedule it. So we waited for an hour, still hasn't gotten a chance to run. It doesn't do any of that. Simply says what is the shortest job and you run. Okay? So the point that was actually being asked is if you do lots of little I/O and simply go back to becoming active, you may starve out CPU bonding. That's exactly an example of always short jobs arriving in the system and starving longer jobs. Yes, question.
Are there any hybrids of SJF and round robin?
Okay, are there any hybrids of SJF and round robin? We are building up, we are getting there. A few minutes. Okay. So good policy, bad properties in some sense. Okay, so it has some good properties, but we don't like the fact that you can never implement it. Okay, that's certainly bad. Okay, and then clearly starvation is something to get rid of. We'll go back to this example. Again, in this case, I'm not going to go through a lot of details. We did these two columns. Okay, this is the shortest job column, same schedule, same jobs. Okay, so you have 5, you pick the shortest job. In this case, you have the luxury of being told the job length. Okay, particularly the kernel doesn't know, but for this exercise, you have been told this. So you will say, you pick the shortest job, that's this one. Okay, you get, it's going to run first, it's going to finish, non-preemptive version. Okay, so it's going to finish, then you run the next one, this one. Okay, of these 4, this is the shortest job, it gets to run this one. Okay. You could also run this in SRTF mode, which I didn't speak about a whole lot. SJF is the non-preemptive version. SRTF does the same thing, but it does one time slice at a time. Okay. So all these 5 jobs have come in, you run the first shortest job, which is this one, you run it for a time slice of 1 second. Okay. At the end of that time slice, you are going to repeat. Okay. In this case, if no new jobs have arrived, the short job that has just run has become shorter. Okay. It went from 10 to 9 seconds because it just ran for a second. All the other jobs haven't run yet. So it's still the shortest job in the system. Okay. So you'll keep doing this. So you'll have the time sliced version, but if there are no arrivals, the short job just gets to run exactly like SJF because it's only getting shorter. There are no other jobs coming, so the other jobs are still at their times. Okay, so SRTF will do exactly the same as SJF. in this case when there are no arrivals in the system. Okay, so I'm not going to spend too much time on this. We'll just see that this finishes at 10, 30, 60, 100, 150. Okay. Okay, the only interesting point now is actually if you take the difference, this is the waiting times. Okay, that's the only instructive thing on this slide. And the wait time is the difference between the completion and the length. And you will see that SJF wait time, the average wait time, that's the mean of those values is 40. Okay? And these two have 80, that's the previous example. I said that this has actually the lowest wait time, and you see that borne out in this example. Its waiting time, average wait time is half of the other policies. Okay, so it did give us very low wait times. Okay? Okay. So maybe this is the last one we'll do, and we'll defer the very last one for next time. Okay, so we have studied round robin. We studied shortest job first. Okay, and in the meantime, there are lots of questions, and I said these are all good ideas. We'll try to put it together into one big policy, and that one we'll call multi-level feedback queue. Okay. This is actually the policy that is used even today by most Unix-like schedulers. MLFQ is its acronym. Okay, there's a reason why this is called MLFQ, and we'll see what it is. Okay, rather than looking at that, let's try to understand some of the ideas. Okay, say we like some things about shortest job first. It reduces wait times. We don't like that it is going to result in starvation. Okay? We also don't like the fact that it's impossible to implement. So you can't really implement it in any particular way. Okay? So we can say, okay, if you cannot actually implement shortest job first, is there a way to approximate it? Try to get something like it, but something that actually can be implemented in your system. Okay, so the multi-level feedback queue is actually going to give us that. It will also take some of the advantages of round robin. We said round robin is fair. It tries to give every job a shot at running on the CPU. We like that. Okay, so we'll try to incorporate that as well. So we'll take the best of these two policies, round robin and shortest job first. Try to get rid of the disadvantages and put together some sort of a hybrid policy that tries to combine the best features. Okay, that's the goal. Okay, but now let's try to think a little bit. Okay, how will you actually try to think about approximating shortest job? If you cannot know the job length, and yet you feel that scheduling a short job somehow actually is the right thing to do because that reduces wait time. What is it that you can actually know? Job length you cannot know. When you start a process, the kernel doesn't know the job length. Yes.
Pass on.
Sorry, what did you say?
I'm mistaken previously.
Past history you can certainly look at. If you say that I ran this application 100 times before and I've looked at what it did and I'm going to use that as an estimator, that you could do. But if this is the first time this job has ever been run, you don't have any history and you don't have the luxury of history to tell you what to do. Then how would you schedule it? Yes.
You could use one of the other two schedulers. First one for serve or round robin.
Okay, we will use round robin in this policy. Okay, but round robin doesn't actually favor short jobs for us. It's just not giving any job priority or any other jobs, treating them all fairly. Okay. Fairness is a good goal. Okay. Trying to finish the short jobs is also a good goal because the one thing I did not mention is why is favoring IO bound jobs a good thing? We just said shortest job first favors IO bound jobs. We didn't say is that good or bad. Okay. And the claim is actually that's a good thing simply because it allows you to maximize the use of both IO and computation. If an IO bound job becomes ready to run, okay, you favor it and say go on and run immediately. So it will use a very short time slice and it will go back to doing its IO and free up the CPU for you to run the longer tasks. Okay. So in this case, the IO bound job doesn't have to wait for a long period of time. It gets priority, it gets to run and it goes back to doing some long burst of IO. And when it's doing IO, it's using your IO resources. Okay. and then the CPU bound jobs can run until the next IO bound job comes in, and it's also maxing out the CPU. So now you are maximizing utilization of both your IO devices and your CPU devices. Okay? So favoring IO bound jobs, regardless of what the policy is a good goal because it tries to maximize the overlap of IO and computation. So we like that about shortest job first. Somehow that's a feature we want to retain in our new policy. Okay? But we don't know the job length. Yeah, we went to this by saying you tell me the job length and I'm going to schedule the shortest job, and it just happened that the ones that are short are simply IO bound jobs. Yes.
As the system gathers more data, does it eventually become an SRTF scheduler?
We would like to make it an SRTF scheduler, but we don't actually know the job length. Not a pure SGF scheduler, the good parts of SGF. We also like round robin. Okay, the first observation we'll make is you cannot know the job length, but the OS kernel can certainly observe what your process is doing. Is it doing IO or not? That you can observe. That you know whether you are actually going to the wait queue or not. Okay, so can we use that observation to design a policy? That what I said clear? I said you cannot know the job length because you don't know when the process will terminate, but you can see what the process is doing now. Is it doing IO? Is it sitting waiting to do computation? That you can actually observe because you can see the process doing what it's doing. So can we use that to our advantage and use it in the scheduling policy? Yes.
Yes, because if you know that a process does more IO than CPU, you could predict that that would be the shortest job.
Okay, that's exactly right. So rather than saying let us schedule the shortest job, and in doing so we are going to favor IO bound jobs, and that's the right thing to do, why not say let's directly favor the IO bound jobs? Forget about job lengths completely. Let's simply observe what the jobs are doing. Okay? They're doing IO, let's give them priority. Those are the short jobs, we know that. Okay? So rather than doing it implicitly by favoring short jobs, let's explicitly favor IO bound jobs. And that achieves the goal. You know which are IO bound jobs. You don't need to be told because you can observe what the job is doing. Is it in the wait queue? Is it doing a lot of IO? That you know. Okay? So our policy is going to achieve shortest job first by not asking for job length, but by blindly favoring IO bound jobs. Okay? If you do IO, you get immediate priority because we label you as a short job. Because you're doing a lot of IO, you must be wanting only short amounts of time on the CPU. Okay? That's an explicit goal. So we are going to approximate shortest job first by not trying to guess the job length. You could have said, I look at past history and say, how did you do? And I'm going to use that as a way to figure out. We will not do none of that. We'll just say, I'm going to observe what you do. Based on what you do, you're going to be treated accordingly. If the job starts doing computation, you lower its priority. Job tries to do more IO, you raise its priority. We assume that job behaviors will change over time. IO bound jobs can start doing computation, vice versa. We'll simply observe what a job does at any given time, okay, and say that's how you might behave in the near future, and we'll treat you accordingly. Yes, question.
So does it have a lowest priority if it has no history, like a brand new process just has the ready queue?
If a brand new process, we give it the max priority. You could say I start with the lowest, but I will start with the max. Okay. So I'm going to take one more minute and end this here. Okay, this is MLFQ. It combines what we just said. It's going to try to explicitly favor IO bound jobs, but it is actually a variant of round robin as well. You basically have not one queue, but you have n queues. Okay? Within each queue, you are going to do round robin. Queues have decreasing priority. Top queue, highest priority. Next highest priority, next highest priority. This is a prioritized scheduler. Okay? Every time the scheduler runs, it starts with the highest priority queue. If that's non-empty, it's going to do round robin here until that queue becomes empty. Okay? When you start the scheduler, if the highest priority queue is empty, you go to the next highest priority queue. If that is non-empty, you do round robin. So within each queue, you do round robin. Across queue, you do priority. Okay? So two features. Within each queue, round robin, across queue, priority. Okay? Now how do we explicitly favor IO bound jobs? Okay? What you do is every time you schedule a job, you simply see what happened in that time slice. Okay? If the job used up its entire time slice, you label the job saying this must be a CPU bound job. I gave it an entire time slice, it didn't do any IO, so I'm going to treat it as a CPU bound job, and you will drop it one level priority. You will decrease its priority until it falls all the way to the bottom. Okay? And you do the reverse for IO bound jobs. You give it a time slice, and if in the midst of the time slice it did IO, you say this must be an IO bound job because it's just done an IO. So you bump up its priority, the next time it becomes ready to run. It will go to the wait queue after it did IO. When it's ready to run, you say this job actually did IO in the midst of its time slice, so I'm going to bump its priority. Okay. So as a result of this policy, all CPU bound jobs will start dropping in priority every time they run, and they will go to the bottom. All IO bound jobs will rise. They will be at the top. This is a prioritized scheduler. You always start at the top, okay, and then you do round robin them. So if IO bound jobs are here, they get to run first. You sort of empty this queue, and then you start looking at the next queues. So the CPU bound jobs get lower priority. That's exactly what SJF also does. But there it reads the job length to do that. Okay, here we are just looking at behavior to do this. Yes, question.
Keep the priority over different times you run the process because it's new each time.
You actually retain the priority. So you always start a new job with the highest priority. Each time slice you see what it did, and based on that you either drop one level or you go up one level. Okay, so you'll always know what your previous priority was, and you will do the right thing. Okay, so basically this is dynamic because if the behavior changes and IO bound job starts doing computation, you start going using its time slice, it will again drop. Or a computational job starts doing IO, it will start rising to the top. So it will adapt based on the changing behavior of application. So you don't need any job lengths anymore. You are still fair because you are using round robin within each queue. Okay? The last point I will say, which was what was the point raised earlier, is as you go down the queue, the priority drop, but the time slice rises. Okay? This has 1 millisecond time slice. Let's say this is 2, that's 4, that's 8. And the reason for this is if you are CPU bound job, why bother doing context switch? Give it a longer time slice, let it run for longer, because all of these jobs are CPU bound. So you reduce the tax you pay. These are IO bound jobs, they anyway need short time slices, so you are going to pick short. So across queues, you have different time slices. So you are also trying to optimize your context switch over, okay, in all of this. Okay. So complex policy uses the best of everything we learned, okay, and also tries to take the best features of shortest job first, the fairness of round robin, tries to reduce context switches, etc. Okay, we are over time. We'll end here. We'll do some examples of MLFQ next time.